and talked a little bit about frequency, and we talked about how it is proportional to speed, in this case the speed of light, and inversely proportional to wavelength, and we kind of just derived that by some simple diagrams here. And now we're looking at this is called, by the way, this is called the visible light spectrum, and all visible light will resemble one of these colors. And here you can see, again, we talked about violet and indigo having the shortest wavelength, so therefore their frequency will be the fastest, and red and dark red are going to have the longest wavelength, so their frequency is going to be slower based on our equation that we just came up with here. And if we wanted to, we can even plug in, for example, if we wanted to see, how, well, let's take, let's look at, we'll do green. We'll say that we have a 500, and say we have a 500, it'd actually be a little lighter than that, 500 nanometer wave. And if we wanted to plug that into our equation, we have to remember that the speed of light is in meters per second. So 3.0 times 10 to the 8th meters per second. And we have to remember that because this is in meters per second, we have to convert our wavelength into nanometers per second. So if we have a 500 nanometer wave and we want to convert it into, I'm sorry, we don't convert it to meters per second, we just need to convert it to meters so that we can calculate the frequency. So to convert 500 nanometers to meters so that it cancels with our speed of light here, we're going to put nanometers on the bottom because we want the nanometers to cancel with the nanometers. In other words, when we divide it, these two are going to cancel. And we're going to put the meters on the top. Meters on the top. And how many nanometers are in 1 meter, or how many meters are in 1 nanometer? You can look at it either way. So for every 1 nanometer, we are going to have 10 to the negative 9th meters. Remember, we talked about that over here. So I'm going to calculate this, and I'm just going to multiply the 500 by 10 to the negative 9th, and that's going to give us 5, and some people can do this in their head, 5 times 10 to the negative 7th meters, right? Because our nanometers canceled and we're left with meters. So now on the bottom of our equation here, we're going to write 5 times 10 to the negative 7th meters, and now we have the same unit. Our meters are going to cancel, and let's plug this into our calculator here. So 3.0 times 10 to the 8th divided by 5 times 10 to the negative 7th, and that gives us 6 times 10 to the 14th, and frequency is typically measured in hertz. So 6 times 10 to the 14th looks like our frequency. Okay, so let's see. So this wavelength, the green one that we just did, which is kind of right about here, that wavelength has a frequency of, this wavelength has a frequency of 6 times 10 to the 14th hertz. If we were to look at the blue wave here, do you think that the blue wave would have a higher or lower frequency than the green wave? Well, if we think about it, the wavelength is smaller, so the frequency must be higher. So the blue wave will have a higher frequency. So frequency is getting higher as we go to a smaller wavelength. Okay? And again, this is another image of the visible spectrum that you can see, the visible light spectrum. And here, this image, which it is kind of congested here, so I'm going to take this and I'm going to move it. I'll just copy and paste it to another section down here. Okay. And this is, as you can see, the electromagnetic spectrum. And this is a little bit different. The visible light spectrum is in the electromagnetic spectrum, but what we're doing is before we were zoomed in. We were zoomed in on this. Before we were zoomed in over here. Now we're taking a step back and we're looking at the whole spectrum. So the visible light spectrum is this section right there that my arrow, let me use a different color, that my arrow is pointing to. So if you, let me use something even darker than that here. There you go. This is the visible light spectrum, this section right here. So the rest of this is the entire spectrum of light. And on the bottom here, you can see that when we calculated, well here, let's look at the frequency. This is the frequency, where it says hertz here. And you can see that the visible light spectrum falls under about 10 to the 14th to about 10 to the 15th hertz. And this is approximately. The light spectrum will approximately fall under that portion. So remember when we calculated the frequency of green light, when we got 6 times 10 to the 14th, that falls right in the middle of this, so that is probably pretty accurate. Now, when we're looking at this whole spectrum, what do we have here? Well, I'm gonna write this a little bigger so you can kind of see. And the beginning of it here, low frequency, you have radio waves. And you can see the radio waves have a really, let me do that again, the radio waves have a really big wave. So the frequency of radio waves is going to be really low, and they're about 10 to the 5th to 10 to the 9th. So radio waves are very low frequency, very long wavelength. And then you have, going across, you have microwaves, you have radar, and now these waves are picking up a little bit. They're going to be a little bit bigger waves, and these are going to be, in terms of frequency, 10 to the 9th to about 10 to the 10th. And then you have millimeter waves, telemetry, and eventually we get over to infrared waves. Infrared. And these are 10 to the 12th to about 10 to the 14th. And now after infrared we go to our visible light spectrum, which is 10 to the 14th to 10 to 15th. And by the way, all of these numbers are in hertz, so this is just representing the frequency. And if you wanted to calculate the wavelength, if you wanted to go backwards, you can always go backwards. Maybe we'll do that in just a second. And use this equation to see what the wavelength is, because we know c is a constant. C is a constant. That's just the speed of light, which always is the same. And nu is the frequency which we're given here. So we can actually calculate what the wavelength would be for one of these waves. And you can see the infrared waves, if you can see this portion that I'm pointing to on the bottom, the infrared waves are going to be a little bit faster. And eventually you get to ultraviolet. Or sometimes we just call this UV. And those are 10 to the 15th to about 10 to the 16th, maybe a little over. And those are getting faster. And then eventually we're going to get to the fastest waves, which are the gamma. Well, first we have X-ray waves, which are not quite as fast as gamma. We have X-ray waves, and then we have gamma waves. And gamma is usually the waves you will get from the sun. So these are getting faster, then they get really fast at gamma, and the gamma waves are actually very, very harmful. This is actually, in developed countries, the leading cause of cancers is from gamma waves, which is radiation from the sun in some cases. So it is a big carcinogen. It's not good for you at all. And we will talk about that at some point in the biology video, what it does to your chromosome and your genes, the mutations it can cause. So that is quite interesting also. But for right now, this is the entire light spectrum, and you should have a pretty good idea as to how the frequency and the speed of light and the wavelength all come together. Let me see. I'm kind of out of room here, so I was going to do an example with the frequency and the speed of light, but simply all we're doing is we're just taking, if we were to find the wavelength of, say for example a gamma ray, if we want to see what that wavelength in nanometers would measure to, it would be very, very small. I mean, because the frequency is really high, as you can see here, the frequency is 10 to the 18th, so the higher the frequency, remember, the smaller the wavelength. They're inversely proportional. So when the frequency goes up, the wavelength is going to go down. So it's going to be a really, really small number in nanometers you would get here that would represent the wavelength for X-rays versus radio waves that would have they would be a lot bigger waves when you compare them to the waves of X-rays and gamma rays. So hopefully this gives you a firm grasp on these concepts. Now we are going to take this information, and in the next video we're going to start applying it to electron kinetics.